Quantities, we've already covered two of them. The two that we've covered are 1 mole is equal to 6.02 times 10 to the 23rd particles. And those particles can be atoms or ions or molecules or formula units. And then the second one is 1 mole is equal to the molar mass in grams. And we've covered this also, which is the molar mass off the periodic table. The third one that we're going to look at today is 1 mole is equal to 22.4 liters for a gas at STP. Now, first we want to talk about what is STP. We've talked about this before. So STP is equal to standard temperature and pressure. So what this means is, in science, we have a standard temperature and pressure. Standard temperature and pressure. So what this means is that scientists have a standard temperature and pressure that they work with. So if I were to say to you, oh, I did this experiment at standard temperature and pressure, then that would indicate the temperature, which is standard temperature, which is 0 degrees Celsius or 273 Kelvin. And so Kelvin is Celsius plus 273. That we learned that, right? That's actually on your periodic table, how to find Kelvin. So you take Celsius and you add 273, right? So our standard temperature is 0 degrees Celsius or 273 Kelvin. Our standard pressure is 1 atm. 1 atm, that's actually like sea level. So our standard temperature and pressure are established. These are just a standard set of these things, all right? And so they're like a baseline. So when we talk about gases being 22.4 liters at this pressure and temperature, it's important to remember that as temperature rises, the volume of the gas expands. If you raise the temperature of a gas, those particles move farther apart, right? And so if they move farther apart, then the volume will expand. If you increase the pressure on a gas, then the volume will decrease because you're squishing those particles together. So by changing the pressure and the temperature, you can change the volume of a gas, all right? By changing the temperature and the pressure, you can change the volume of a gas. So when we set the temperature and the pressure at a standard, we can say with consistency that the volume of this gas will be 22.4 liters. If carbon dioxide is at 0 degrees Celsius and 1 atm, there will be 22.4 liters of it. And again, wrapping your head around that is hard, so let me put it in some terms that we can understand. If I have 22.4 liters, 11 2-liter bottles, okay, and I don't have the tops on them, and they're filled with carbon dioxide, and they're just sitting there, and I don't have the tops on them because the carbon dioxide is sitting comfortably in these bottles. It's not escaping, and it's not sucking in more. It's just sitting there comfortably in these bottles, right? And the bottles are full, and they're just sitting there leveled off. About 11 1/4 2-liter bottles, that gas is at 0 degrees Celsius and 0 degrees Celsius and 1 atm. And it's all just sitting there, nice and comfortable. If I raise the temperature, those particles will spread farther apart and the gas will start to escape from those bottles because raising the temperature will increase the volume. If I decrease the temperature, they will move, but particles will move closer together and more of those particles will go into the bottles. But at this temperature and this ATM, that gas will take up 22.4 liters of volume. 11 and a quarter 2-liter bottles. All right? Now, all gases that we work with, they're called ideal gases, will equal that, 22.4 liters. And so therefore, we can set up a conversion that 1 mole is equal to 22.4. 1 mole is equal to 22.4 liters at STP. All right? So we have a conversion now between volume and liters. Between volume and moles. And that comes in handy because now you know how many particles there are and everything else. As long as it's at this temperature and pressure. We have an entire chapter on gases where we change the temperature and pressure. And that changes the volume and it changes the number of moles that we can hold and everything else. But for right now, we're always at STP, okay? And 22.4 liters of gas, only gas, not liquids or solids, is equal to 1 mole, okay? So that's the conversion. Got it? All right. So now let's take a look at an example problem because here are your first conversions that you've been using. Particles can be anything, atoms, molecules, formula units. Here is the second one, and here is the new one that we just learned. Now, using the factor label method, just means conversions. That's not a term that I use. It's kind of an older term. I don't use that term. You weigh a 24-karat gold chain, and you find that it weighs 400, and there is a decimal point here. It's here, but it's not here. 400 grams. Determine how many moles of gold atoms you have. So we start with the grams of gold. We put grams on the bottom and 1 mole on top. Super easy. You guys are already doing that at home by yourself, right? And you get 2.03 moles of gold. But what I want to do is I want to up the game a little. What if we have 400, right, grams of gold, and now I want to know how many atoms of gold that is. All right, so we're kind of upping the problem a little bit here. And so what we're going to do is we're going to start the exact same way. Grams of gold. So I'm going to start with 400 grams of gold. But now, to get to atoms, I have to go to moles. Why? Because the only way that I can get to particles here is by getting to moles. To going from 1 mole is 6.02 times 10 to the 23rd atoms. So I have to get from grams to atoms, to moles. So I'm going to do the exact same thing that I did here. 196.97 grams of gold to 1 mole of gold. And then I'm going to go from moles of gold to atoms of gold. So 1 mole of gold has 6.02 times 10 to the 23rd atoms of gold in it. And that's how I've gone from grams to atoms. I can cancel out grams and I can cancel out moles and I'm left with atoms. Now, the reason I did this is because you get to see both grams to moles and moles to atoms in the same equation. And so that's kind of helpful. Now, if we're going to do the calculation on this, if I'm going to do the calculation on this, I'm going to take 400 times 6.02 E23, and then I'm going to equals divided by 196.97, the mass of the gold. And that's going to be 1.22 times 10 to the 24th. All right? Atoms of gold. Questions? All right. Okay, that's all I've got for you. Now, so you're going to be doing this worksheet today. You're starting with like moles, atoms to moles, and then the other side is molecules in moles, and then grams and moles and grams, and then down here, these last three, moles to liters at STP. So when it says at STP, you know you're doing 22.4 liters to 1 mole. Okay? That's where that conversion comes in. All right, you can get started. You may work with whom you want. I would work with somebody that you're going to be productive with, right? Ella? So particles is whatever is relevant. So it could be molecules, it could be formula units, it could be atoms, it's whatever they're asking for. So if they say like, how many moles of magnesium is in this many particles? So that would obviously, since it's magnesium, it's going to be atoms, right? How many in glucose? That's going to be molecules, right? Okay. All right, get started. If you have any questions, just come on up. All right, and you may change seats if you want to work with who you want, whatever you want to do.